All right, we've talked about the definition of the probability generating function, and we've gone through the calculation. We've gone through and cataloged the generating function for some well-known discrete distributions that we've seen before. So now let's talk about some of the properties of generating functions that makes them special and makes them easy to work with. I'm not going to prove all these necessarily. They should be pretty clear in a lot of cases. And if I don't prove them, what I don't prove, you can prove as an exercise. Okay. So first is let's let, of course, as always, let's preserve the notation. G sub x is the generating function for x. Okay. And let's define y to be a plus bx. I do want to correct something. It is not required that x be an integer valued random variable. It just has to be non-negative and discrete. Okay. Turns out that the discrete non-negative random variables we deal with are generally integer valued, but they don't have to be to technically define the generating function. So if y is a plus bx for constants a and b, then the generating function of y can be expressed in terms of the generating function of x. How? Well, it's z to the power a times g of x as a function of z to the power b. Okay. This should be a straightforward exercise, but let me just show you. I'm going to sketch here and then I'm going to erase this. So g of y, by definition, is the expectation of z to the power y, but y, by definition, is z a plus bx. Z a plus bx is z to the a, z to the bx. Z to the a is a constant. We can pull that out of the expectation. Z to the bx can also be written as z to the b to the power x. So here we have z to the a, and then this expression here is exactly the generating function of x, but evaluated at the value of z to the power b. So that's exactly how you would do that calculation. That's exactly how you would prove that. It's just using properties of the expectation that we've already established. And so I ran through that relatively quickly because you should be able to reproduce that on your own as an exercise. And I would encourage you to do that if anything there didn't seem straightforward. We have independent random variables x and y. Generating function of y of x plus y is the product of the generating functions. We've seen this in action already twice because we've seen that we know that the binomial is the sum of n independent Bernoullis. We know what the Bernoulli generating function is. So the sum of n independent Bernoullis, the generating function of that is the product of the Bernoulli n times. And we see that here, where we see that the binomial is the Bernoulli generating function raised to the power n. And that's by property of the expectation that we've seen before. For a positive integer n, the probability that x is equal to n is the nth derivative of g evaluated at 0. And this is where g superscript, and we're defining this as the nth derivative of x with respect to z. Okay, so that's where the definition, that's where the term generating function comes from, is that you can generate the entire distribution of the x's. You can generate the entire distribution of the x's by taking the derivatives and evaluating them at 0. This does require x to be integer valued, though. And then the next property is that, again, for n non-negative integer, the nth derivative of the generating function evaluated at 1 is the nth factorial moment of x. And in particular, the first derivative evaluated at 1 is equal to the expectation. So these need to be proven, and you should prove them as exercises because we have all of the tools that we need to prove them at this point. And what I'll do now is I'll go through an example in the case of the Poisson distribution. So let's let x be a Poisson random variable with parameter lambda. Then we already have shown that the generating function is e to the lambda z minus 1. Okay. Let's take derivatives of this with respect to z. It's easy to take derivatives of e to the lambda z minus 1, right? This is an easy thing to take derivatives of. This is, again, why this shows why these are so easy, so convenient, is that sometimes, a lot of times, not always though, the generating function is very easy to work with in terms of taking derivatives. So we take derivative of e to the lambda z. This is really just, the first derivative is lambda times e to the lambda z minus 1. The second one is you take another lambda down. You take another lambda down. So you end up with lambda to the n e to the lambda z minus 1. So what do you get? Well, this might be, okay, this is off. So this is, I'm sorry, this is a typo up here. Probably the next equal to n is gx is the nth derivative evaluated at 0 divided by n factorial. You have to divide by n factorial. So now let's use that in the case of the Poisson. Evaluate this at 0, we get lambda to the n e to the lambda 0 minus 1. Okay, so this is lambda to the n e to the minus lambda. And the nth derivative evaluated at 1 is lambda to the n e to the lambda 1 minus 1. So it's just lambda to the n. So as we've already seen before, well, we know that probability of mass function, probably that x equals n is lambda to the n e to the minus lambda over n factorial. This is the nth derivative of the mass function evaluated at 0 divided by n factorial. And we've already seen before also that the n factorial moment of the Poisson is just lambda to the power n. So this is a very convenient, very quick way to derive expectations of all moments of the Poisson distribution. And then let's consider x1, x through xn independent Poisson lambda 1 through lambda n respectively. Then the generating function of the sum by independence is the product of the generating functions. Each generating function is e to the lambda 1 z minus 1 times etc. e to the lambda n z minus 1. Product of exponentials, you can add up the exponents. So it's e to the sum lambda 1 up to lambda n times z minus 1. This is the generating function of a Poisson random variable with lambda 1 with intensity with parameter lambda 1 plus the sum of the lambdas. And the uniqueness theorem tells us then that sum of independent Poissons are Poisson with sum of the parameters, the sum of the individual parameters. And this is another way, a very easy way, we've already proved it before, to prove the reproductive property of the Poisson distribution, which also is related to the superposition property of Poisson point process. So everything kind of starts to work together here. This is one specific example of sums of random variables, and we're going to do an example in which we have a random sum of independent random variables, and we'll do that next. And there's a very easy way to handle this using generating functions, as we'll see.